Hey guys, so in our discussion of one-dimensional motion, I think it's important to derive the kinematic equations that we will actually use. Um, Also for two-dimensional stuff. I plan to do that in two different ways. So let's go ahead and get the kinematic equations, derivations out of the way. Okay. Um, So I'll start with the algebraic version. Okay. And how this will start is I'm going to start with the definition of velocity. So if you remember, velocity and also average velocity equals the time derivative of position. Okay. And another way to write that is delta x over delta t, right? But what else was delta x and delta t? Well, delta x and delta t was equal to x final minus x initial over time. Okay. And so what else can you do with this? Well, we can get a form that is fairly useful for us where we solve for the final from this. Okay, so we have v equals x final minus x initial over time, where that's an average velocity. Okay, get rid of that. And so now we can just go ahead and solve. So what we do, average velocity times time is x final minus x initial, and that leads to, if we do that, we get x final equals x initial plus v times t. That is equation number one. Okay, pretty useful equation actually. You use this one actually quite a bit. Okay. Let's go ahead and derive another one. Now, this derivation actually isn't much of a derivation. It's pretty much just the definition of average, which is the initial velocity plus the final velocity divided by 2. This is considered a kinematic equation, even though there wasn't much of a derivation to it. So the third one, since we used velocity, the definition of velocity to derive the first couple equations, what we're going to do now is use the definition of acceleration then. So acceleration, which is typically average acceleration, but since there is no change in acceleration because we always deal with constant forces, we don't have to put anything above it. I guess we could put a vector hat to denote it's a vector, but it's not important in the derivation. So we pretty much do the same thing we did before. V final minus V initial over time. Okay. And again, this is for constant A. All of these are pretty much for constant A. Okay. And we go ahead and solve for final velocity. V final equals V initial plus AT. Okay. So that's equation 3. So equation 4, okay. Apologies for my neighbor's dog who I suppose they, do not know the meaning of training. What we can do is actually go ahead and take V equals V naught plus AT, the equation we just derived, okay? And what we can do is add V naught to each side. Again, apologies for the disturbances there. So V final plus V naught equals 2 V naught plus AT. And now what we're going to do is divide by 2. And you must be thinking, well, what are we actually doing here? We're getting into a form that's actually fairly useful. Okay. And then, do you remember what this guy is? This guy was just v bar. Okay. So then we get v bar equals v naught. Whoops, sorry. That should have been 1/2 up there when you divide by 2. Oops. Okay. Killing me. Okay. So that's 1/2. That carries down. Thought it looked odd. Okay. So now we have this form. Okay. But what we can also do is, do you remember what else this guy was equal to? Well, we also have, okay, we also have x equals x naught plus v bar t. And we can go ahead and solve for that. X minus x initial over time equals v bar. So now what we can do is plug this in. Ugh. Undo. We can plug this in right there. Okay, so let's go ahead and do that. So we have x minus x initial over time equals v naught plus 1/2 at. Now we can go ahead and multiply everything by t. Okay. So x minus x initial, so we'll just multiply by t. V naught times t plus 1/2 at squared. And then we can get our final form by adding over our x naught. X equals x initial plus v naught t plus 1/2 at squared. Okay. We can also add an x final there because that's what it actually is. And this equation right here is probably the quintessential equation. What equation number is this? 4. Yeah, it's equation 4. Okay. This equation is super useful. You'll probably use it for most situations where you have something exposed to a constant force. In one-dimensional motion, you're always exposed to at least some constant force. Otherwise, you don't really have too much to talk about. Okay. So now we can go back. So for the final equation, for equation 5, we start with v equals v naught plus at. Solve for time. Okay. And so v minus v naught divided by a equals time. Okay. So now what we want to do with that is we want to plug that in. Basically, we want to plug that into this equation. Plug t into v bar. Plug this into, sorry, x equals x naught plus v naught t. And we'll plug in t there. But more than that, we also want to plug in v bar equals v naught plus v over 2. Right there. So let's go ahead and do that. Okay. So we have x equals x naught plus v naught plus v over 2. And remember, anytime this doesn't have a subscript, it's actually v final. Okay. And then we just do what time was equal to. And I believe, what was time equal to? Let's see here. Time was equal to v minus v naught over a. v. Okay, and then we get our final form where we get x, which we can call x final, equals x naught, plus v naught v minus v naught squared plus v squared, which is v final, minus v naught. Now these guys commute, so they're done. And this is all over 2a. So now we get our final equation, x equals x final plus v final squared minus v initial squared over 2a. Okay. And you may see this in a different form. Most famously, it's typically written if you multiply the 2a over. So first off, actually, let's do this. Let's do the x final minus x initial, v final squared minus v initial squared over 2a. We multiply that 2a over. And there's a reason we do this. It's basically because it's its most useful form. Okay, so then we just do v final squared equals v initial squared plus 2a x minus x initial. You may also just see this as, delta x or whatever. And this is our equation 5. Okay. And this is also with constant a, just as a reminder. So these are all constant acceleration. So we have a summary here of our 5 equations. So we have x final equals x initial plus that. We have v bar equals v initial plus v over 2. That one's the least useful. We have v final equals v initial plus at. We have x final equals x initial plus v naught t plus 1/2 at squared. And we have v final squared equals v initial squared plus 2a x final minus x initial. Constant a on all of those. So those are all the equations. Okay. So what I will do in the next edit, I will go ahead and derive these equations, or at least derive the main one, this guy, from a constant force. So from Newton's second law, I'll derive these. Okay. Thanks.